Good morning, guys. Myself Sridhar H, working as the assistant professor in the Department of Electronics and Communication Engineering at Government Engineering College, Haveri. Okay, today in the session 9, that is registers and counters of a basic electronics, module 5, digital electronic fundamentals. So in this session, we are just going with the registers. Okay, shift register. Shift register. What is shift register? Shift register is a group of flip-flops used to store multiple bits of data. Okay, so the flip-flop already we know that it is having a storage elements. So people are trying to store the multiple bits of data. Stored bits the bits stored in such registers can be made to move within the registers and in and out of the register by applying clock pulses. Means whatever the values means the stored values will be having, so it can be shifted right or left. That is, it can be moved by applying a clock pulses. An n-bit shift registers can be formed by connecting n flip-flops, where each flip-flop stores a single bit of data. Okay, I already know that single flip-flop will be having only a single, it can store only a single bit of data. So if you want to have n-bit data, then it will be using a n number of flip-flops. The register will shift the bits to left are called shift left registers, and if you are shifting by right, then it is called as shift right registers. Okay, so we can move left shift or a right shift. Shift registers are basically of four types. These are serial in, serial out shift register, that is SISO, CISO. Next, serial in parallel out register, serial in parallel out, that is SIPO, SIPO. Next is parallel in serial out shift register, PISO, PISO. Next is parallel in parallel out shift register, PIPO, PIPO. Okay. Next, so we will be having, so what we people are just going with the SIPO, that is serial in parallel out register. So we are just moving with a 4-bit parallel data output. So we are using 4 flip-flops, flip-flop A, flip-flop B, flip-flop C, as well as flip-flop D. Okay, see, a common clock is being given to all the flip-flops. Serially data will be sent, means it will be just sending a one by one data. Initially all the flip-flops, we can assume all the flip-flops value as 0 0 0, and we can directly send a serial data in. So at the once clock, all the outputs will be getting at a same time. So we will be getting a serial in parallel out. Means initially when the clock will be, all the flip-flops output will be 0. If I just give a clock, at that time what I will be getting, all the outputs will be just 0. If I next, for the next clock, if I just move or send one data, then it will be what, 1 0 0. Okay, next whatever the input will be getting, that is, if I just once again 1 doing the next second clock cycle, what will happen, the whatever the output I am getting here 1, that will be shifted to here, and the next input whatever I am giving is here, that is, I will be getting after the clock is what, 1 1 0 0. In this fashion it will just go on moving. And when the clear button means, once I give a clear button, at that time whatever the stored value will be having, once again it will be reset to 0 0 0. Okay, next, the same thing it has been explained now. Let's assume that all the flip-flops, flip-flop A to flip-flop D, have just been reset clear input to all the outputs, QA to QD at logic level 0, no parallel data outputs. Okay, means once initially when the clear button is been given, so what will be happening, whatever the flip-flops value or the data, whatever it will be stored, all it will be changed to a 0 value, that is QA, QB, QA, QC and QD will be having all the 4 outputs as 0 0. If a logic 1 is connected to data input pin, serial data in, that is the data input pin, then on the first clock pulse the output of flip-flop A, and therefore the resulting output is set to high, with other outputs will remain low at logic 0. As I told initially, what, when if I just want to give the serial data it as 1, during the first clock what will happen, the 1 will be shifted to here, the whatever the value that is stored in a flip-flop, that output will be getting it as 1, remaining all 3 bits will be what, QB, QC and QD will be 0 0 0. The same thing it has been explained here. Here will be set to high logic 1, with all other outputs still remaining low at logic 0. Okay, next, the second clock pulse will change the output of flip-flop A to logic 0 and the output of flip-flop B and QB high to logic 0, as the input D has the logic level on into a form. Okay, see, what we are doing is we are just giving only the one input. Okay, after the next what it is happening, the same 1 is been shifted to here, next is the 0 will be having, so that the second pulse the output will be what, QA will be 0, QB will be 1, QC is 0 and QD is 1. Okay, next at the next clock pulse what will happen, at the third clock pulse this 0 is shifted to here, this 1 is shifted to here, and whatever the stored value is 0 it is being shifted to here, that is QA is 0, QB is 0, QC is 1 and QD is 0. And at the fourth clock what will happen, 0 0 0 1. See the same thing during the fifth clock, that is the first, initially all the clocks will be what, set to 0. During the first clock what it is happening, the first initial QA is 1 0 0, next at the second clock 0 1 0 0, the third is 0, is this 0 is been shifted to here, this 0 is been shifted to 1, that is 1 is been shifted here. Next, so whatever the value, this 1 will be 0. See here. Next, once again the 0 is been shifted to here, so this 0 is 0, this 0 is shifted to here, this 1 is shifted to here. Once again the next clock pulse what will happen, once again, so 0 if I just give the value, so this will, that this one is the initial data, so this 0 is shifted here, this 0 is shifted here, so this 0 is shifted here. So this will not be having until for the next clock pulse, if they give the input as 1, then only the 1 I will be getting, or else only 0 will be just shifting. See, during the positive clock pulse, initially what, all the bits will be 0. During the first positive clock pulse, 1 is been 0, remaining all bits will be 0. During the second clock pulse what is happening, this 1 is being shifted to here and the remaining bits all will be 0. During the third clock pulse this 1 is being shifted to here, and during the fourth clock pulse this 1 is being shifted to here. Okay, the same. After the clock pulse, 4 bits of data, that is 0 0 0 1 are the stored in the register and will remain the provided clocking of the register head flop. If we just stop the clock at that time, it will be having the value 0 0 0 1, or else if we just once again give the clock input with the input as 0, then the next state will be what, 0 0 0 0. Simple use of shift register is that if I just give the value 1 0 1 1 0 0 0, okay, during the first clock pulse or initial clock what it will having, at the clock pulse is 0, all the bits will be just stored to 0 0 0. Next, during the first clock pulse what it is having, I am sending this data at as 1. Okay, so 1, remaining bits are all 0 0. Next, during the second clock pulse I am giving this output as data in, so this 0 I am just giving here. Next, this one is been shifted here, this 0 is shifted here, this 0 is shifted here. Next, during the third clock pulse what I am giving, the 1, so if I just give the 1, so this 0 is shifted here, this 1 is shifted here, this 0 is been shifted. Next, once again when I give the input as 1, so what is happening at the fourth clock pulse, 1, this 1 is shifted here, this 0 is shifted here, this 1 is shifted here. Next, once again when I give the clock as 0 input, at the fifth clock pulse what it is 0, this 1 is shifted, 1 is shifted, 0 is shifted. In this fashion we are just going on giving the input. At the last 8 is what, all the 8 bits will be 0. See here, the output what we will be having is what, as soon as we just give the inputs at this 1 0 1 1, all 4 zeros, and the output what we people are looking at, the output is what, 0 0 0 0. So this one is just the serial in parallel out shift register. So if this sequence can be anything, whatever the sequence will be, just it is just shifting towards the next clock pulse, whatever the value will be from the first previous flip flop to the next flip flop. Binary counter. A binary counter is a hardware circuit that is made up of series of flip flops. Okay, the output of the flip flop is sent to the input to the next flip flop in the series. A binary counter can be either asynchronous or synchronous depending on how the flip flops are connected together. So whether the clock is being connected to all the flip flops, or the flip flop is acting, the flip flop output is acting as a clock to the next input, depending upon what it is being asynchronous or a synchronous. The count output of 9-bit binary is 2 raised to n states. 2 raised to n, where n is number of flip flops. So the free flip flop counter will have a maximum count of 2 cube is equal to 8 counting states. So depending upon what number of flip flops, we are just mentioning how much the counting states. If the counter goes from 0 to 2 raised to n minus, then it is called a binary up counter, and if the counter counts from down from 2 raised to n minus 1 to 0, then it is called a binary down counter. that is 2 raised to 8 count means it should be counting from 0 to 7 for up counter, and for down counter it should count from 7 to 0. If I just count the counting states of 8, that is 2 cube. Asynchronous counter. In asynchronous counter, different flip-flops are triggered with the different clock, not simultaneously. Asynchronous counter is slower than synchronous counter in operation. So why we people are going for asynchronous counter or synchronous counter is asynchronous counter is slower than the synchronous counter. Asynchronous is also called as serial counter. Asynchronous counter designing as well as implementation is very easier, though it is very much slower, but it is easier to design and it is very easy. Asynchronous counter will operate only in a fixed count sequence, up or down. So we can't work in both the condition up and down. We can just design a synchronous counter in for up counter or down counter separately. Asynchronous counter are ripple up counter, ripple down counter. Next, we'll just cross check with the 3-bit ripple counter. The 3-bit ripple counter asynchronous binary up counter contains 3 T flip-flop. See, 3-bit ripple counter is so where people have been using for 3 T flip-flop, and all the flip-flops are connected to 1. See, 3 T flip-flops have been taken, okay, and all the T flip-flops are connected with the one value, logical value. Okay, see, since it is a asynchronous, only the first flip-flop clock is been given, and the output of the first flip-flop is acting as a clock to the next flip-flop. See, the Q1, then the next clock flip-flop, output of a clock flip-flop is acting as a clock to the next flip-flop. The output of the previous flip-flop is acting as a clock to the next flip-flop along with the output. That is, so this one if I just get Q0, Q1 and Q2 are the output. All 3 flip-flops are negative STO, but the output changes asynchronously. The clock signal is directly applied to the first T flip-flop. The output of the T flip-flop toggles for every negative edge of the clock signal, and it is depend upon the designer whether people are going for a positive edge or a negative edge. See, in the 3-bit ripple counter, what we are doing is we are just connecting 3 flip-flops, and the T0, T1 and T2, all the T inputs are being connected with logical value. Only for the first flip-flop we are just giving it a negative edge clock, and the next flip-flop, the output of the first flip-flop is acting as a clock to the next flip-flop, that is the second flip-flop, and the output of the second flip-flop, that is Q1, is acting as a clock to the next flip-flop. The output of the first flip-flop is applied to the JK for the second flip-flop. So the output of the second T flip-flop toggles for negative edge of the. So see here, Q2 toggle for negative remains, otherwise remained in the previous state. So whatever the people have been just going, so Q2 toggles for every Q1 that goes from 1 to the other remained in the previous state. The initial state of the previous in the absence of clock signal is Q2, Q1 and Q0 is equal to 0. So initially what it is having Q2, Q1 and Q0 will be having what initially 0 value. This is increment by one of the negative edge of the clock signal. It is to maximum value of 7th negative of the clock signal. So we just going on giving the clock. So whether we people are be designed for up counter or down counter, depending upon that we people are be just going. 3 ripple. Okay, see the first initially what of the negative edge clock. So during the initial clock what it will be having, it will be all having bits to a 0 0 0, that is Q2, Q1 and Q1. During the next clock is happening only the 0 0 1. So that is the first flip-flop output will be just considered. See here, Q0, Q2, Q1, Q1. The first initial output is what 1. So I am getting here. Okay, the value will be what 0 0 1. Next, during the second clock what happened, this T is been toggled here, so what it will be having 0 1 0, and during the third what is happening, this 1 is been shifted to here, so what it is having 0 1 1. So next once again when it is T is happening, what it is happening is 1 0 0. In this fashion the clock will be having, and during the 7th clock what it will be having is the 7 value, that is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So Q2 for every Q1 that goes from 1 to otherwise remained in the previous state. The initial state of the state in the absence, okay, the same thing what it is being when it is moving from 1 to 0 or 0 to 1, that it is just cross checked. Okay, the timing diagram of triple means here. during the negative edge of clock, what it is having is all the three inputs are being 0 0 0. Once again during the negative edge clock, what it is happening is 0, that is 0 0 1. During once again the negative edge, what happening 0 1 0. Next 0 1 1. Next here it is 1 0 0 1 0. So this just go on to the next bit. When one bit changes from 1 to 0, next bit should toggle. Okay, depending upon that we will just consider. Next, module 5 ripple counter. So this one is a normal 3-bit ripple counter. Now people are going for module 5. Module 5 or a mod 5 ripple counter means it should count for the 5 states. That is, if you are taking for module 5, then it should count from 0 to 4, and then when it reaches the 5th state, once again it changes to a 0 state. Okay, the minimum number of flip-flops used in counter is given by 2 raised to n minus 1, that is 2 raised to n state. Thus, for mod count 5 counter, 2 raised to square is equal to 2 cube. That is the value what we will be having. Mod 5 means we will be having a 7 state 0 to 7. That is a 8 state condition. As we are constructing a mod 5 counter, we want the counter to reset back to 0 after a count of 5. As soon as it reaches a 5, then it should move to the next state. However, you can see from the attached table that the count of 6 gives up to a condition of QA is equal to 0, QB is equal to 1, and QC is equal to 1. That is, as soon as it reaches the 1 1 0, it should go to a 0 0 0. Then it should count for 1 0 1. Okay, see 0 1 1. That is 1 1 0. As soon as any one of the input is 0, what will happen to the NAND gate? All the inputs will be just clear, so it should go into the clear state. The inputs of the combination logic circuit of the inverter and AND gates are connected to QA, QB, and QC respectively with the output of the AND gate and logic level for any combination of the input. In binary code, the output sequence count will look like this: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, and 1 0 1. But when it reaches the state of 6, 1 1 0, okay, count 5 means you are counting for 0 1 2 3 4 and 5. But when it reaches the state 6, that is 1 1 0, the combination of logics will detect this 1 1 0 state and produce the output logic level 1 as high. So see the NAND gate has been connected along with the inverter, so 1 1 1 is high. Clear. If the clear is high, what will happen? All the states have been changed to the next once again to a 0 0 state. The resulting high output from AND gate to reset the counter back to 0 after its output 5 decimal count, giving us the mod 5 counter with the output from the conventional circuit is low, then it is not having the sequence here. The same counter whatever giving is here. So normal clock is been given to the first clock pulse. Okay, next what is having? The D input has been just connected with the T, and the Q output is acting as a clock to the next flip flop. The output of Q is acting as the second is acting as the input. Okay, now what people are doing in, so the output whatever people are getting, that value is just taking, okay, Q bar value, since it is of a negative edge, is not this thing. So whatever the value will be having 1 1 0 0 means we people are being connected with the NOT gate along with this, and this whatever the output of AND gate is being connected, that we are connecting with the clear button. Okay, as we just connecting with the clear button means as soon as it reaches 1 1 0, 1 1 0, that is 0 means 1, 1 1 means the NAND gate or AND gate output is what? 1. As soon as the clear button is 1, once again it should set back to a reset 0. Okay, see a clear result pulse QA, QB, QC. Just we are just going on 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1. Next, as soon as it reaches 1 1 0, the reset button is high. Okay, that is the clear button or the reset button is high. Once again, it should confirm what? 0 0 0, next 0 0 1. In this fashion, let's go on continuing. If they ask for mod 3, then what will be having? So just be considering what? 0 1 1. Okay, 0 1 1. That is counter of a output will be what here, the 110. So that will be just changing from 110, that is 0 1 1. Next, mod 6 asynchronous up counter. Mod 6 counter will require 3 flip-flops and count from 000 to 101. Here T flip-flop has been given, the output of this Q has been connected, so 000010001. As soon as it reaches 101, the output has been connected with the clear. Once the counter reaches 101, next positive edge of the clock will make the all the three inputs of NAND gate as 1. See here, 1 0 1. So all the three inputs as a 1. See here, QI is 1, okay, 0, and the clock button is being connected with the this one. As soon as it reaches the thing, what we'll be having is we are just connecting the need 0 button is not being connected. 1 0 1, only QA and QC are being connected along with the clock. As soon as it reaches 1, it is been 0. Okay, so as soon as it reaches the 0, once again the counter starts from 0 0 0. So we are just connecting for with the NAND gate. So whatever the outputs are being here, so QA is 1, QC is 1, only these two are being connected along with the clock. Along with the clock they have been connected. Next, asynchronous down counter, same thing. What is happening? So we are just connecting with the output of a Q bar to a clock. So in this up counter, what it means, the output positive means the positive Q output has been connected as acting as the clock to the next input. For down counter, what we are doing is we are taking the Q bar output is acting as the clock to the next input. See, that is the only main difference between up counter and down counter. For up counter, Q output of Q was acting as a input clock. Okay, for down counter, Q bar is acting as a clock input. Next, synchronous counters. In synchronous counters, the external clock signal is connected to the clock input of every individual flip-flop within the counter, so that all the flip-flops are clocked together simultaneously in parallel at the same time, giving a fixed time relationship. In other words, changes in the output occur in synchronization with the clock signal. Okay, so what is happening is, so all the flip-flops are clocked together at the initial one clock only. All the flip-flops are been connected and in parallel at the same time given a fixed time relationship. In other words, changes in the output occur in synchronization. As soon as the clock is been given, the changes should be happening at the same time. The result of the synchronization is that all the individual outputs bits changing state at exactly the same time in response to the common clock signal with no ripple effect and therefore no propagation and delay. So why the synchronous counter very fast means, as soon as the clock is given at a single clock, all the outputs are being just changing, means whatever the flip-flops are being connected, the same changes at the flip-flop states will be changing at the same times here. So common clock is being given to all the flip-flops. 4-bit synchronous up counter. Okay, that we are just cross checking which up counter is this. Flip-flop is toggle so on every clock pulse. This flip-flop Q0 is high. This flip-flop Q0 and Q0 is high. This flip-flop toggles only when Q0 and Q1 and Q2 are high. Since they have been just giving with the NAND gate, so they will be just connecting. Okay, just what to remember in this 3-bit synchronous up counter is what? A common clock is being connected. Okay. See here, the synchronous up counter. So what it is happening is, by using the AND gate, we have been connected to the next J and K input. Okay, external clock pulse pulses to be counted are fed directly to each of the JK flip flop in the counter chain, and both the J and K inputs are all tied together in toggle mode high. But only in the first flip flop FFA, that is a LSB, that is the least significant bit. See here, only for this one it has been just connected with the allowing the flip-flop to toggle on every clock pulse. Then the synchronous counter follows a predetermined sequence of states in response to the common clock signal, advancing one state for each pulse. As soon as the pulse is been given, the clock signal will be just changing. Next, the J and K inputs of flip-flop FFB are connected directly to the output QA of the flip-flop A. Then the and gates which are also supplied with the signals. If we enable each JK flip-flop to toggle based on whether or not all preceding flip-flops outputs Q are high, we can obtain the same counting sequence as with the asynchronous circuit. but without ripple effect, since each flip-flop on this circuit will be clocked at exactly the same time. Then there is no inherent propagation delay in synchronous counters here. What it is having a common pulse is been given. So QA it is having a state of 1 by 1. Next QB will be what? The separate pulse will be having at QC, longer delay as well as the QDC. So what is the output of the count is what? 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1. Next 0 1 0 0 0 1 0 1 0 1 1 1. Next 1 0 triple 1. Next is what? 1 0 0. In this fashion, 4-bit synchronous counter waveform diagram will be just cross checked. So QA will be what? Your LSB, and QD will be your MSB. A common clocks here. 2 to 3 it is having rise. Next it is being shifted to this one, the second B. The third is the C, QC, and fourth is the 4. After 4 clock 8 pulses, that is each pulse is having of a 2 to 3. That will be joining. After 8 pulses, what is having is a high for the next 8 bit, that is a 0 to 8 and 8 to 16. So this one is the up counter. Next synchronous down counter. We can easily construct 4-bit synchronous down counter by connecting the AND gates to the Q output. Okay, and the flip-flop has shown to produce the waveform timing diagram the reverse of the above. See here, the AND gate was being connected at the top, and now it has been connected to the bottom with the Q bar output. So that is the only thing what we people are the main changes here. Synchronous decade counter. Decade counter means what? It should be counting from 0 to decade counter means it should count for the 10 counter, that is it should count from 0 to 9. A standard binary counter can be converted to a decade 10 counter with the aid of the some additional logic to the input. After reaching the count of 101, that is 9, 1 0 0 1, that is 8 plus 1 is 9. The counter recycle back to 0 0. We now have a decade module counter. See here. So what we people have been just checking is for 1 0 0 1. So 1 whatever you will be getting is what? For a NAND gate AND gate output. So 0 0 we have not been taking considering here. Next once again this one at a clock. So at this point it is acting as a modulo 10 counter. Synchronous decode. The additional AND gates detect then when the counting sequence reaches 0 0 binary 1 0 and causes flip flop to toggle on the next clock pulse. Flip flop FF0 toggles on every clock pulse. Thus the count is reset and starts over again to 0 0 0, producing synchronous decade counter. See, a normal QA to QB has been connected with the AND gate, QB to QC, and a separate clock has been just connected along with the OR gate. So as with that 1 0 0 1, it has been just counting with the clock pulse. Okay, so this one is a synchronous decade counter. So it will be counting from what? 0 0 to 9. Okay, thank you.